Think about the last time you tried to push something heavy. Maybe it was a refrigerator, maybe a table. You leaned into it and felt resistance immediately, as if the object itself was stubborn. We're used to calling that weight or mass, and we treat it like a basic property, something objects simply have. But if you stop and really think about it, that answer explains nothing. It just replaces one word with another. Physics isn't satisfied with that. Physics always asks what lies underneath. For centuries, people assumed mass was fundamental. An object had it the same way it had a color or a shape. End of discussion. But when scientists began probing nature at smaller and smaller scales, that simple picture started to break down. The deeper we looked, the less the world resembled solid chunks of matter, and the more it looked like patterns of activity. Tiny interactions, exchanges of energy, vibrations spreading through something more subtle than stuff. In that picture, mass is no longer obvious. It becomes a question. To understand that question, we need to start with something that sounds strange at first. Empty space is not empty. If you remove the air from a box, then remove every atom, then strip away radiation, you don't end up with nothing. You end up with a stage where physical properties still exist. Space can stretch, it can store energy, it can respond to disturbances. In modern physics, we describe this by saying that space is filled with fields. A field is not an object you can hold. It's more like a condition that exists everywhere. Think of temperature in a room. At every point, the temperature has a value. Or think of the wind. You don't track individual wind particles. You describe how fast and in what direction the air is moving at each location. Fields in physics work the same way. They exist throughout space, assigning values everywhere whether or not particles are present. Once you adopt this viewpoint, particles themselves stop looking like little beads. Instead, they become localized vibrations in fields, like ripples moving across the surface of a lake. This shift in perspective quietly introduces the logic of calculus. Fields vary smoothly from place to place, so understanding them means understanding change. Calculus is simply the language we use to track how things vary across space and time. Light offers an important clue here. A beam of light carries energy. It can push objects, heat surfaces, and transfer momentum. Yet it has no mass. No matter how energetic light becomes, it always travels at the same speed. You can't make it sluggish by adding energy to it. That's deeply strange if you think mass is just a measure of how much stuff there is. Electrons, by contrast, do have mass. They resist acceleration. Push on them and they respond slowly compared to light. But both light and electrons are excitations of fields that fill space. Both are disturbances in something that exists everywhere. So why does one behave as if it's heavy while the other behaves as if it's weightless? That question troubled physicists for decades. The mathematical descriptions of nature seemed to work best when particles had no mass at all. Whenever mass was inserted directly into the equations, the theory lost its internal consistency. But reality clearly contains massive objects. Tables exist. People exist. Something in the theory had to change. The solution came from an idea that sounds almost philosophical, but is extremely practical. Symmetry. Symmetry means that certain changes don't affect the laws of physics. Rotate a circle and it looks the same. Perform an experiment today or tomorrow, and the underlying rules don't change. Demanding symmetry limits what theories can allow. It simplifies possibilities but can also make things tricky when the real world doesn't appear perfectly symmetric. A useful example is a pencil balanced upright on its tip. In that moment, every direction is equivalent. The situation is symmetric, yet the pencil never stays that way. It falls, choosing one direction and breaking the symmetry. The laws didn't change, but the outcome did. This phenomenon, called symmetry breaking, turns out to be crucial for understanding how particles acquire mass. To see why, imagine a landscape of hills and valleys representing energy. A ball balanced at the top of a hill sits in a symmetric position, but any tiny disturbance sends it rolling into one of the valleys. Once there, the symmetry is gone, even though the landscape itself remains unchanged. In physics, fields have similar energy landscapes. They settle into configurations that minimize energy, just as the ball settles into a valley. The lowest energy configuration of a field is called its vacuum state. That term can be misleading because it doesn't mean emptiness. It means the calmest possible arrangement. Space itself is filled with this settled field the way a room is filled with air. You don't see it, but everything moves through it. And once you start imagining motion through such a background, a new possibility appears. Not every disturbance moves through that background in the same way. Some pass through almost unnoticed, gliding freely as if nothing is there. Others interact strongly, feeling resistance as they move. That resistance shows up to us as inertia, the reluctance of something to accelerate. A simple picture helps here. Imagine walking through a quiet, empty room. You move easily, barely slowed at all. Now imagine crossing a crowded hall where people cluster around you, asking questions, blocking your path. From a distance, it would look as if you had suddenly become heavier, harder to move, but nothing was added to you. The change came from interaction with the environment. Modern physics suggests that mass can arise in a similar way. It isn't something stored inside a particle like coins in a pocket. Instead, it can emerge from how that particle interacts with a field already present throughout space. The particle is not intrinsically heavy. It behaves as if it is heavy because of how it couples to this background. This idea resolved a long-standing theoretical problem. The laws describing fundamental forces could remain beautifully symmetric and consistent, while particles could still acquire mass through their interactions with a field that does not vanish even in empty space. The vacuum itself is structured. It has a preferred configuration, and moving through it can be easy for some excitations and difficult for others. You may notice that calculus quietly returns here. When physicists speak of energy landscapes and lowest energy states, they are describing the points where change stops, where slopes vanish. Calculus gives us the tools to locate those stable points and understand how systems settle there. Nature, of course, does not perform calculations explicitly. It simply evolves toward configurations that minimize energy. So we arrive at a picture in which space is filled with a field sitting in its calmest state. Particles moving through that state interact with it to different degrees. Some barely notice it and behave like massless waves. Others couple strongly and appear heavy. Mass, in this view, is not a built-in property, but an emergent effect of interaction. Now, if a field fills all of space, it can also vibrate. Just as the surface of a lake can ripple even when calm, a field can experience small disturbances around its settled value. In modern physics, every particle corresponds to such a disturbance. Electrons are vibrations of one field. Light is a vibration of another. This rule holds universally. Particles are not separate objects placed into space. They are patterns in fields that already exist everywhere. The field responsible for generating mass is no exception. Its vibration is another particle, one that appears only when enough energy is concentrated in a region to disturb the field significantly. Most of the time, the field simply sits there, quietly shaping how other particles move. But under extreme conditions, its vibration can briefly emerge. It is tempting to treat such a particle as something mystical, as if it carried special significance beyond the physics. That temptation should be resisted. Physics is not about sacred objects. It is about mechanisms. The importance of this vibration lies in what it confirms, that our framework of fields, symmetries, and interactions is largely correct. Even so, understanding always opens further questions. Why does this field have the particular form it does? Why does it settle at one value rather than another? Why do different particles interact with it differently? Physics does not hide these uncertainties. It places them front and center because each unanswered question marks a direction for future exploration. What we have learned already is remarkable. Mass, once assumed to be a primitive property of matter, appears instead as a consequence of interaction. It is a kind of resistance arising from motion through a structured vacuum. When you push a table and feel it push back, you are not just encountering solid material. You are encountering fields, symmetries, and energy landscapes working together. The next step, naturally, is to ask how we know any of this is real. How do you test the existence of a field that fills all of space? How do you detect a vibration that lives for only an instant and leaves no direct trace? Those questions lead us to extraordinary machines and careful experiments. Physics never accepts an idea simply because it sounds elegant or satisfying. Nature must agree, and the only way to know whether it does is to test the consequences of the idea. That is where the real challenge begins. A field that fills all of space cannot be bottled or weighed. You cannot point to a spot and say, "There it is." Fields are known only through what they do. Think again about the wind. You never see wind itself. You see leaves moving, clouds drifting, flags snapping. From those effects, you infer that something is happening in the air. In the same way, the field responsible for mass reveals itself through its influence on particles. But influence alone is not enough to prove the specific theory. Physics always asks what else must follow if the idea is correct. One unavoidable consequence is that the field must be able to vibrate. If a field exists, disturbances of it must also exist. This is not optional. It follows directly from the mathematics describing how fields behave. And every disturbance of a field appears to us as a particle, so the existence of the field predicts the existence of a corresponding particle, not because anyone wanted it, but because the logic of the theory demands it. This predicted particle is unlike most others we encounter. Particles such as electrons or photons travel long distances, forming beams and leaving tracks in detectors. The vibration associated with this field is different. It is heavy, unstable, and extremely short-lived. It appears only when large amounts of energy are packed into a very small region of space. Why is it so difficult to produce? The answer again lies in the energy landscape of the field. To create the vibration, the field must be pushed away from its calm value. That costs energy. The steeper the energy valley surrounding the calm point, the more energy is required to make the field wiggle. In everyday terms, that steepness corresponds to a heavy particle. Calculus hides in this idea as well. When physicists speak about the curvature of an energy landscape, they are describing second derivatives, measures of how rapidly slopes change. A steep valley resists displacement strongly. A shallow one allows easy motion. Even without equations, you can feel this distinction. Stretch a stiff spring, and it resists strongly. Stretch a loose spring, and it yields easily. The field responsible for mass sits in a very stiff valley, so disturbing it requires enormous energy. To supply that energy, physicists build particle accelerators that collide particles at tremendous speeds. This is not extravagance, it is necessity. Only by concentrating enough energy in one place can the field be shaken hard enough to reveal its vibration. When particles collide, their kinetic energy can reorganize into other forms. This transformation is not magic. It follows the rule that energy is conserved even as it changes form. In these collisions, the field itself is not created. It was already present. The collisions merely excite it. For a fleeting instant, the vibration appears before quickly decaying into other particles. Detecting it directly is almost impossible. Instead, physicists look for the pattern of its decay products. They measure the directions, energies, and frequencies with which other particles emerge after collisions. This is where statistics becomes essential. Any single collision could be misleading. Nature is noisy, and many processes produce similar outcomes. Confidence comes only from examining enormous numbers of events. Patterns that consistently appear more often than chance predicts begin to stand out. Physicists analyze distributions, averages, and probabilities, searching for signals buried in vast amounts of data. Science often looks dramatic from the outside, as if discoveries happen in sudden flashes. In reality, they usually emerge slowly. A small excess of events here, a consistent pattern there, agreement across multiple detectors and analyses. Only when all lines of evidence converge does the community begin to trust the result. When the evidence finally becomes convincing, the discovery is not celebrated as the finding of a single particle. It is celebrated as confirmation of an entire framework. A framework in which fields fill space, symmetries guide laws, and mass emerges from interaction rather than being inserted by hand. And once that framework is supported, the story does not end. In physics, confirmation is never the final step. It is the beginning of better questions. If a field explains how particles gain mass, we immediately want to know why that field has the properties it does. Why does it sit at one value rather than another? Why do some particles interact with it strongly, while others hardly notice it? These are not decorative questions. Small changes in those interactions could have produced a universe where atoms never formed, stars burned differently, or chemistry as we know it never existed. Physics does not answer these mysteries with appeals to purpose or design. Instead, it openly admits what remains unknown. That honesty is essential. Good physics does not claim to know everything. It narrows ignorance step by step, building reliable structures while recognizing their limits. Every explanation applies within a certain domain, and beyond that domain, new puzzles appear. Another lesson concerns how easily names can mislead. When ideas become famous, they often acquire dramatic labels that work well for headlines but distort understanding. A name can suggest that something is more profound than it really is, or more mysterious than necessary. In physics, no particle is sacred. Each one is a clue about how nature organizes itself. Some clues are central, others peripheral, but none deserve reverence. Nature does not arrange itself to impress us. It simply behaves according to consistent rules. The field we have been discussing is important not because it occupies a special philosophical place, but because it solves a technical problem cleanly. It allows particles to have mass without breaking the symmetries that make our theories coherent. That may sound modest, yet modest solutions often prove the most powerful. Nature tends to favor efficiency over spectacle. At this point, it is worth reflecting on what understanding really means. Many people assume that to understand physics, you must be able to picture everything visually. That is helpful sometimes, but not always possible. Fields, for instance, are difficult to draw or imagine literally. We rely on metaphors, a crowded room, a lake's surface, a landscape of hills and valleys, but those are tools for thinking, not reality itself. True understanding lies in knowing which questions are meaningful and which explanations fit the evidence. One essential feature of this picture is universality. The field fills all of space. It cannot be switched off in one region and left on in another. Every particle everywhere interacts with it to some degree. Mass is not an optional attribute that objects choose to have. It arises from the conditions of the universe itself. At the same time, interaction is selective. Some particles couple strongly to the field and appear heavy. Others interact weakly and remain light. This selectivity is built into the theory. We do not yet know why those interaction strengths take their specific values. We simply observe them and incorporate them into our models. That diversity of interaction is what allows structure to exist. If everything behaved identically, there would be little complexity in the universe. As we step back, a broader pattern emerges. Physics continually shifts our focus from objects to relationships. Instead of asking what something is in isolation, we ask how it interacts with everything else. The deeper we look, the more reality appears as a network of processes rather than a collection of separate things. This perspective can feel unsettling because it replaces solid foundations with interconnected dynamics. But nature does not promise simplicity, it offers consistency. It is also important not to exaggerate the role of this field. Most of the mass of ordinary matter actually comes from other effects, such as the energy stored in the interactions of smaller constituents. Even without this field, protons would still be heavy. The field is crucial but not exclusive. It is one component of a larger structure, a necessary piece rather than the entire building. Beyond that structure lie further mysteries. Gravity does not yet fit comfortably into the same framework, nor does the unseen matter that appears to dominate the universe's mass while barely interacting with light. These questions remain open. If you are hoping for a final, complete theory neatly tied together, physics may disappoint you. It builds scaffolding, some parts solid, others provisional, all subject to revision. That flexibility is not a flaw, it keeps the field alive. So what should you take from all this? Not the name of a particle or the details of an experiment, but a way of thinking. When you push against the world and feel resistance, remember that this resistance is not a primitive fact. It reflects interactions with fields that fill space. When you hear that something exists everywhere, picture not a substance, but a condition. When you encounter a mysterious entity in physics, ask what problem it solves. Most importantly, remain comfortable with uncertainty. Confusion is not the enemy of understanding. It is often its beginning. Nature is subtle, but it is not deceptive. If we ask clear questions and listen carefully, it gradually reveals how it works. Not instantly, not effortlessly, but honestly. And in the end, that honesty is the most reliable guide we have for exploring the universe.